Unfortunately, I wrote right where the projector is going to show, but we looked at gave you a couple homework problems with this, and this concludes the material for this exam. Okay, but we need to work through a couple of example problems on frequency response here. And I do have practice exam. This is the exam I gave last year, so I'll hand that out before we leave today. I guess I'll leave that up and try to work around this. Okay. So I think I assigned 2.29 as homework. And here's a case where you're given the frequency response of a system. It's 1 over j omega plus 3. And we're asked to find the output for these different cases. And this we do know, this is one of the few frequency responses we know corresponds to that impulse response. That's the only one kind of that we've derived at this point. And then we also have, you know, from the differential equation, we can come up with a frequency response. So how would you suggest we solve for the output when the input is equal to 1? Well, this, we could use convolution, and we can see if we can get the same result. But this is a special case of e to the j omega t with omega equal to 0, right? Omega equal to 0 there, e to the 0 is 1. And actually, you know, I didn't put in here, you know, if x of t is 2e to the j omega t, y of t would be 2e to the j omega t, h of omega. That's a linearity property. Or if the input is 10 cosine, the output would be 10 absolute value of h omega cosine. And that's a linearity property. Here, with this input, it's a special case of this exponential input with omega equal to 0. So I just evaluate the frequency response at omega equal to 0. What is that? This is the easy one. So they get tougher at other frequencies. What is this with omega equal to 0? That's a third. Right? So y of t here is h of 0 times x of t, or just in this case, it's 1/3 times 1, or 1/3 would be the output. I mean, if we wanted to do it by convolution, here's h of, I'm going to jump directly to the tau part. This is h of tau, it's e to the minus 3 tau. This would be the u of t. X of tau, x of t minus tau. So x of t is 1 everywhere. I time reverse that one and shift it, and it's 1 everywhere. Now, how do I compute the output, well, remember it's the integral from minus infinity to infinity of the product of these two. Now, this thing doesn't change as a function of t, right? X of t minus tau actually doesn't change at all as a function of t. So I integrate from minus infinity to infinity. The product here is 0. Well, I'll leave it like this. X of t minus tau, d tau. But h of tau is 0 between minus infinity and tau equal to 0, so my lower limit changes to 0. And for tau greater than 0, 1 times e to the minus 3 tau. It's just that. So that becomes minus 1/3 e to the minus 3 tau, evaluated at 0 and infinity. It's a tau. Evaluated at infinity, I get 0. Minus evaluating it at tau equal to 0, I get 1. So I get 0 minus 1/3 or 1/3. So I get the same result. It's a lot easier to do that than using the frequency domain approach. Now, B, x of t is 3 square root of 2 cosine of 3t. Okay. So what's the frequency of that sinusoid? What's the frequency of the input? Here it was 0. What is it for this input? Yeah, it's 3. Omega is 3 radians per second. So we need to evaluate, now it's a little harder, h of 3. It's not much harder. That would be J3 plus 3. Okay. Now you could do this with your calculator at this point. I encourage you to do that. Pull out your calculator and evaluate 1 over J3 plus 3, 1 over 3 plus J3. But this would be 1/3 over 1 plus J, or the magnitude of the denominator here would be square root of 2. And 1 out, J up would be 45 degrees, but it's 0 minus 45 degrees. So if you get something like this on your calculator, the angle, I hope that would be whatever that is, over square root of 3. Square root, I don't know where that came from. Square root of 2, right? Magnitude of 1 plus j is square root of 2. We should have got that on your calculator. And so y of t then is x of t times, well, for the sinusoidal input, I take the magnitude. So the magnitude of h of 3 is just 1 over 3 square root of 2. And then the phase angle, of h of omega is minus 45 degrees. So y of t with this sinusoidal input is this times that. Well, that just cancels out. So I'm left with, it's the same frequency, but now phase shift. Okay, so that would be the output. I guess one thing to notice here, that with the linear time invariant system, you know, whatever frequency I put in, I get that same frequency out. Right? That's what this is telling me. If this is 2t, I get out 2t. If it's 100t, I get out 100t. There can be a change in amplitude and a phase angle, but the frequency doesn't change. So, any questions about that? What's the next one look like? I'll give you a few minutes to work on C here. The input is 5 cosine of 4t. The way I wrote down for A, x of t was actually 3 in the problem. So this should have been 1/3 times 3, and then 1 is the answer. Right, for part A, I wrote down x of t is equal to 1, which is actually f. But in the problem statement there, it says x of t is equal to 3. Write that down now. Okay, so in this one, the input is 5 cosine 4t, the frequency is 4 radians per second. Now, if it were 5 e to the j 4t, I would just get out 5 e to the j 4t times h of 4. Okay. But I need h of 4. Here I need the magnitude phase. We'll look at that. Okay, so h of 4 is h of omega. It's 1 over j4 plus 3. And want to evaluate that on your calculator?
0.2 e to the minus 53.1.
You got what? 0.2?
Yes.
E to the 53.1?
Yes.
think that's right. Because the magnitude would be of the denominator is 5. It's a 3, 4, 5 triangle. So the 1/5 is 0.2. And then the inverse tangent of 4/3 is 53.1. Okay, so 53.1, you put the degree symbol up there. If there's no symbol, it's the radians. Okay. So that means y of t is 0.2 times 5. Well, I'll write it all out through. And then same frequency minus 53.1 degrees. Or 1 cosine of 4t minus 53.1 degrees. Okay? If it were, let's just say if it were this, e to the j 4t, y of t would be h of 4, 0.2 e to the minus j 53.1 degrees times the input, 5 e to the j 4t. And that's going to be e to the j 4t minus 53.1 degrees. If the input were that. And the real part of, if I take the real part of the input, it's 5 cosine, right? If I take the real part of this, it's cosine 4t minus 53.1. That would kind of be the other way to do this, actually, is find the output to the corresponding complex exponential. Take the real part. Okay, D, I can't write, it's an impulse. I can't write that as, it's not a sinusoid. It's not a complex exponential. The only other way to know how to solve the problems like this at this point is a convolution. So, but for that, we don't want h of omega, we need h of t. This is the only kind of h of t frequency response that we have at this point. What am I going to get as output when the input is delta t, when the input's an impulse? So when the input is an impulse, what do I get out? What's the response to an impulse? The impulse response, which is h of t. Remember, this is actually what I get out when I input to my system delta t, part c. So this would be the output to delta t. If it were 2 delta t, I'd get twice this. If it were delta t minus 1, I would substitute t minus 1 in here and here. But here it's just a simple impulse at the origin. By definition, I get out the response, the impulse response. So this would be the answer to D. C, and it's a unit step, which I can't represent as a complex exponential, a sinusoid or a sinusoid. So convolution again. Good. Now I'm convolving u of t with this, but that's in our convolution table. And then D is similar to A. I could do convolution like I did here, or do it in a frequency domain. Or I'm sorry, F. F is the same as the output for F will be 1/3 the output to A. So for, I think 230 I also assigned as homework. Just come up with the corresponding frequency response here. The numerator will be 5j omega. The denominator will be j omega squared, which is minus omega squared, plus 2j omega plus 7. Okay. We're feeding it, at the input is 2 cosine t. Then the output, I have to find out what h of 2 is. I evaluate that at h of 2. Get the magnitude phase. The magnitude would give me the amplitude. And there's corresponding phase shift. Is that okay? Okay, let's look at maybe some of these other problems. See if we can figure out what's going on here. Now, remember, because of linearity, I can break these. If we look at 236, I can break this down into a sum of inputs, right? And then I said, when we feed cosine t, we get a cosine t out. When I feed it cosine 2t, I got to get a cosine 2t out. When I feed it a constant, which is something at 0 frequency, I've got to get a constant out, okay, or 0. So that, since when I fed it this constant, there's no constant at the output, that tells me h of 0 has to be 0. I don't know what h of 0 is. I don't know what h of omega is, but I know h of 0 is 0. What's h of 1? Evaluate the frequency response at omega equal to 1. It has to be 3, right? There's no phase shift, okay, because the phases here are the same. But h of 1 has to be 3. Because I look at this, which has a frequency of 1, the output is 3 times larger. H of 2 has to be 2, just a real number, again, because there's no phase shift. Now, I don't know h of omega, in general, but I know h of omega at 3 frequencies, 0, 1, and 2. Now, fortunately, they said, we'll find the output with this input. Fortunately, it's composed of the same 3 frequencies. If it weren't, I'd be out of luck. Okay. What would be the output in response to 4 for this system? Be 0, h of 0, 0. What would be the output in response to 4 cosine t? It's going to be 3 times larger, 12 cosine, and then no phase shift. And the response to 2 cosine 2t would be 4 cosine 2t. What would be the response to cosine of 4t? Don't know. There's not enough information here. I'm not given h of omega. I don't know it. I know what it is at those 3 frequencies. Let's take another case. So let's say x of t, something maybe a little bit harder, is 2 cosine of 3t plus 45 degrees. In response to that, I get 4 cosine of 3t plus 90 degrees. Can you tell me what h of 3 is? It has to be 2e to the plus j 45 degrees. Right? Because y of t is the magnitude of h of 3, which is 2, times the amplitude of x of t to get my 4. And then I have to have a 45-degree phase shift added to 45 to get 90. So what would be the response to 10 cosine of 3t? Be 20 cosine of 3t plus 45 degrees. I couldn't tell you what it is. With this information, I couldn't find the response to cosine of 10t or anything like that. I only know h of 3. Okay. So in some of these problems, we're given h of omega. Okay, and so I can find it at any frequency. And some of these problems, I only know it at a few frequencies. Let's see, I think what's 37 look like here? Okay. Then 37, I know, this part has to give me this part. Now this is not a cosine or an exponential, but it's got to give me the rest. Okay. So u of t has to give me this part. This sinusoid has to give me this part. And then so h of 2 has to be, looks like 1 over square root of 2 at an angle of minus 45 degrees. And then this is at the same frequency. And this is just a time-shifted version of this. So the output has got to be a time-shifted version. This has to give me this. This has to give me that. So if this is the response to u of t, what's the response to 5, u of t minus 3? It's got to be 5 times this, because it's 5 times larger. That's linearity. And then time invariance tells me, well, this is just delayed by 3, so this has got to be delayed by 3. So this has got to be u of t minus 3 minus e of minus 2 times t minus 3 times u of t minus 3. Any questions about any of the homework? Okay, let's, got a few minutes here. So you can work together on these. This is the exam I gave last year in this class over the same 2 chapters. So our exam's on Monday. I expect, I'll give you that convolution handout. If you notice, it says closed text, closed notes. You can use a calculator and a pencil. Okay. And then I'll give you that convolution pair table and properties. So the first one is actually function composition. Coming up with a mathematical expression for the given function. Well, start working through this, and we'll go over it on Friday. This is your homework for today. So come back with this completed on Friday. Stop.